Ladies and gentlemen, what if intelligence could step off the screen and into the real world, able to see, to move, to work, and to learn alongside us? What if the limits of human effort were no longer defined by fatigue, danger, or repetition, but expanded by machines built to amplify our potential? Today is not about imagination or distant promises. It is about a future being built right now, where artificial intelligence gains a physical form, where software learns to act, and where the way work gets done is about to change forever. And the announcement that a working Tesla bot would be revealed at AI Day 2022 represents a defining moment in the evolution of artificial intelligence, robotics, and real-world automation. This moment is not about speculation or distant science fiction. It is about taking ideas that once lived only in research labs and bringing them into the physical world, where they can interact with people, environments, and complex tasks in a meaningful and safe way. The focus is not on novelty, but on utility, scalability, and long-term impact on how work is done. And the Tesla bot concept is built on the same foundational philosophy that drives every major product: first principles thinking, vertical integration, and rapid iteration based on real data. Instead of designing a robot as a standalone experiment, the approach leverages years of experience in AI, computer vision, neural networks, hardware design, energy systems, and manufacturing at scale. The result is a humanoid form factor optimized not to look human, but to function in a world designed for humans. Doors, tools, factories, homes, and infrastructure already exist at human scale, and a robot that can navigate these environments without requiring the world to be rebuilt around it has a clear practical advantage. And revealing a working Tesla bot at AI Day 2022 signals a transition from concept to reality. A working prototype demonstrates locomotion, balance, perception, and task execution, all powered by neural networks trained on real-world data. This is the same AI backbone used in autonomous driving systems, repurposed and expanded to handle a broader range of physical interactions. Vision is central. Instead of relying on expensive, fragile sensors, the system prioritizes camera-based perception combined with advanced neural networks that understand depth, motion, and context. This allows the robot to interpret its surroundings in a way that is adaptable, scalable, and continuously improvable through software updates. And at the core of the Tesla bot is the belief that AI should be useful. The goal is not to create a robot that performs a single impressive trick, but one that can eventually handle repetitive, dangerous, or monotonous tasks that people should not have to do. From carrying objects and assembling components to assisting in logistics, manufacturing, and eventually household tasks, the potential applications are vast. The emphasis is on tasks that are physically demanding or time-consuming, freeing human effort for creativity, problem-solving, and innovation. And safety is a foundational principle. A humanoid robot operating around people must be inherently safe by design. This means limiting size, weight, and power output to human-compatible levels, ensuring that the robot can be easily stopped, overridden, or avoided. The control systems prioritize smooth, predictable motion and constant environmental awareness. By designing the robot to be slower and weaker than a human, at first the system builds trust while allowing software intelligence to improve over time. Intelligence scales faster than mechanical strength, and that order of progression matters. And the reveal at AI Day 2022 also highlights the strength of a software-first approach. Hardware provides the platform, but software defines capability. Neural networks trained on massive datasets enable the robot to recognize objects, understand instructions, and adapt to new situations without explicit reprogramming for every task. Over time, learning from fleet data allows rapid improvement, similar to how autonomous driving systems evolve. Each deployment becomes a source of insight, accelerating progress across the entire system. And manufacturing expertise plays a critical role. Designing a robot that can be produced at scale requires deep integration between engineering and production. Materials, actuators, batteries, and control electronics are optimized not only for performance, but for cost, reliability, and ease of manufacturing. This is where experience in building millions of complex machines becomes a strategic advantage. A robot that cannot be manufactured efficiently remains a research project. A robot designed for mass production becomes a product that can change economies. And energy efficiency is another key factor. A humanoid robot must operate for long periods without excessive power consumption. Advances in battery technology, power electronics, and energy management enable extended operation while maintaining a compact form. This efficiency is essential for practical deployment in factories, warehouses, and eventually homes. It also aligns with a broader mission of sustainable energy use, ensuring that increased automation does not come at the cost of increased environmental impact. And the broader implications of a working Tesla bot extend beyond robotics. It represents a shift in how AI is applied to the physical world. Intelligence is no longer confined to screens and servers. It moves, lifts, navigates, and interacts. This convergence of AI and robotics has the potential to reshape labor productivity and quality of life. Tasks that are currently limited by human physical endurance can be automated while humans focus on higher-level decision-making and creativity. An AI Day 2022 serves as a platform to share not just the result but the process. Transparency in development invites collaboration, attracts talent, and accelerates innovation. By showing a working system, the message is clear: progress is driven by execution, iteration, and a willingness to tackle hard problems directly. The Tesla bot is not presented as a finished product, but as a rapidly evolving platform that will improve through continuous learning and deployment. And the vision behind revealing a working Tesla bot is grounded in practicality. It is about building machines that are genuinely useful, scalable, and aligned with human needs. It reflects confidence in the idea that AI, when paired with thoughtful design and responsible engineering, can enhance human capability rather than replace it. The working prototype is a milestone that demonstrates what is possible when advanced software, efficient hardware, and large-scale manufacturing expertise converge in a single system. And this convergence also introduces a new way of thinking about intelligence as a physical utility rather than an abstract capability. Intelligence becomes something that can be deployed where it is needed, when it is needed, and improved continuously through feedback loops. A working Tesla bot embodies this idea by existing at the intersection of perception, decision-making, and action. It sees the world, understands intent, and responds with precise movement. That loop, repeated millions of times, forms the foundation of real-world intelligence. Each iteration refines accuracy, efficiency, and reliability, turning complexity into something manageable and predictable. And one of the most significant aspects of this development is the reuse of an existing AI stack that has already been tested at scale. Autonomous systems require the ability to process massive amounts of visual data in real time, make safety-critical decisions, and operate under uncertainty. These same requirements apply to a humanoid robot navigating dynamic environments. By adapting and expanding, this stack, development accelerates dramatically. Instead of starting from zero, the system builds upon years of data collection, neural network training, and real-world validation. This creates a compounding advantage where improvements in one domain reinforce progress in another. And the working Tesla bot also reflects a philosophy of simplifying the problem before solving it. Rather than attempting to replicate every nuance of human motion immediately, the focus is on stability, balance, and basic manipulation. Walking, turning, lifting, and placing objects are treated as engineering challenges that can be solved incrementally. Each solved problem unlocks the next level of capability. Over time, fine motor control, faster response times, and more complex task execution emerge naturally from improved hardware and smarter software. And another critical dimension is adaptability. Real-world environments are messy and unpredictable. Objects are not always where they are expected to be, lighting conditions change, and humans behave inconsistently. A useful robot must handle this variability without constant human intervention. This is where neural networks excel. Instead of relying on rigid rules, the system learns patterns and generalizes from experience. A working prototype demonstrates that this approach is viable beyond simulations in real physical spaces with real constraints. And the economic implications are substantial. Labor shortages, aging populations, and increasing demand for productivity create a clear need for automation that goes beyond traditional industrial robots. A humanoid form factor allows deployment without redesigning entire workflows or facilities. The same robot can potentially be trained to perform multiple roles, switching tasks through software updates rather than physical reconfiguration. This flexibility reduces costs and increases return on investment, making advanced automation accessible to a broader range of industries. And at the same time, the emphasis remains on collaboration rather than replacement. The Tesla bot is envisioned as a tool that works alongside people handling tasks that are undesirable or unsafe while humans retain oversight and control. This collaborative model increases overall output without diminishing the value of human contribution. By removing physical strain and repetitive labor, it enables people to focus on planning, creativity, and interpersonal interaction, areas where human strengths are most pronounced. And the reveal at AI Day 2022 also underscores the importance of speed in innovation. Building a working system quickly allows real-world testing, early feedback, and rapid iteration. Problems that are invisible on paper become obvious in practice, and solutions evolve faster as a result. This bias toward action is central to making ambitious ideas tangible. A working robot, even with limitations, provides more insight than years of theoretical discussion. And from a technical perspective, actuator design plays a crucial role. Smooth, efficient movement requires motors and gear systems that balance power, precision, and durability. Advances in custom actuators allow fine control while maintaining energy efficiency. Combined with intelligent control algorithms, this enables natural, stable motion that can adapt to uneven surfaces and unexpected disturbances. Each improvement in actuation feeds back into better control, creating a virtuous cycle of refinement. And thermal management and reliability are equally important. A robot expected to operate for hours each day must manage heat, wear, and environmental exposure. Lessons learned from electric vehicles, energy storage systems, and power electronics inform these designs. Components are selected not only for peak performance, but for longevity and ease of maintenance. This pragmatic approach ensures that the system can transition from prototype to product without fundamental redesign. And the working Tesla bot also serves as a platform for future capabilities that extend beyond physical labor. As perception and reasoning improve, the robot can begin to understand higher-level instructions, interpret context, and prioritize tasks. Natural language interfaces, gesture recognition, and adaptive learning open the door to more intuitive interaction. Over time, the barrier between human intent and robotic action becomes thinner, making the technology more accessible and less intimidating. And scalability remains a central theme. Building one impressive robot is not enough. The goal is to build millions of them, each benefiting from shared learning and continuous improvement. Software updates propagate instantly, raising the capability of the entire fleet. Data collected from diverse environments enriches training, making the system more robust with each deployment. This network effect is difficult to replicate without deep integration between hardware, software, and data infrastructure. And the societal impact extends into education and workforce development. As intelligent robots become more common, new skills emerge around supervision, training, and system optimization. Rather than eliminating opportunity, this shift creates demand for roles that blend technical understanding with human judgment. The technology becomes a catalyst for redefining work, emphasizing adaptability and lifelong learning. And the decision to reveal a working Tesla bot at AI Day 2022 is ultimately about confidence in execution. It signals belief in the underlying technology, the development process, and the long-term vision. It demonstrates that artificial intelligence can move beyond screens and simulations into the physical world in a controlled, purposeful way. Each step forward reinforces the idea that progress is not achieved through grand declarations, but through building, testing, learning, and building again. And this iterative loop defines how complex systems mature from early capability into dependable infrastructure. Every deployment becomes a real-world experiment, generating data that sharpens perception, improves decision-making, and refines movement. Unlike static machines, a humanoid robot benefits from cumulative experience. Each object lifted, each step taken, each interaction observed contributes to a growing understanding of the physical world. Over time, this learning transforms uncertainty into confidence and novelty into routine execution. And a critical advantage lies in unifying intelligence across platforms. The same neural networks that interpret traffic flow, recognize obstacles, and anticipate motion can be adapted to understand human activity, workspace layouts, and object dynamics. This shared intelligence creates consistency across systems and accelerates progress. Improvements in vision accuracy or motion prediction immediately enhance performance everywhere they are deployed. This compounding effect is central to scaling intelligence efficiently. And the design philosophy emphasizes minimalism and purpose. Every component exists for a reason, optimized for function rather than spectacle. The humanoid form is not an attempt to replicate human appearance, but a practical solution to navigating a human-built world. Hands are designed to grasp common tools, arms to reach standard heights, and legs to step over obstacles and climb stairs. This practicality ensures relevance from the start, avoiding dependence on specialized environments. And as capability increases, task complexity naturally expands. Initial functions focus on material handling, simple assembly, and logistics support. These tasks are repetitive, physically demanding, and time-intensive, making them ideal candidates for automation. As confidence grows, the same system can transition into more nuanced roles, such as quality inspection, maintenance assistance, and adaptive manufacturing support. Software updates enable these transitions without hardware changes, preserving investment and extending usefulness. And the relationship between autonomy and supervision is carefully balanced. Full autonomy is not a prerequisite for value. Even semi-autonomous operation can dramatically increase productivity when paired with human oversight. This hybrid model allows gradual expansion of responsibility as reliability improves. Humans remain in control, defining goals and constraints, while the robot executes tasks with precision and consistency. And energy management remains a foundational constraint and opportunity. Efficient movement is not just about speed or strength, but about minimizing wasted effort. Intelligent planning reduces unnecessary motion, while optimized hardware converts electrical energy into mechanical work with minimal loss. These efficiencies extend operating time, reduce costs, and enable sustained deployment in real-world settings. They also reinforce broader goals of responsible energy use and sustainability. And the working Tesla bot also demonstrates the importance of simulation paired with reality. Virtual environments allow rapid testing of scenarios that would be impractical or unsafe to replicate physically. These simulations generate training data, validate algorithms, and expose edge cases. When combined with real-world testing, they create a feedback loop where virtual insight informs physical improvement and physical experience refines virtual models. And reliability underpins trust. For a robot to be accepted in shared spaces, it must behave predictably and recover gracefully from errors. Redundant systems, continuous monitoring, and conservative decision-making ensure safe operation even when conditions deviate from expectations. When uncertainty arises, the system prioritizes caution, slowing down or stopping rather than forcing action. This approach builds confidence and establishes a foundation for broader adoption. And as production scales, cost reduction becomes a force multiplier. Custom-designed components simplified assembly, and supply chain integration reduce unit costs over time. This trajectory mirrors the evolution of other complex technologies that began as premium innovations and eventually became accessible at scale. Affordability expands application, driving further data collection, and improvement reinforcing the cycle of progress. And the implications for global productivity are significant. Many industries face constraints not from lack of demand, but from limited labor availability or unsafe working conditions. Intelligent robots can operate continuously in environments that are uncomfortable or hazardous for humans. This capability increases output while reducing risk, improving both economic efficiency and worker safety. And human interaction remains a central design consideration. A robot operating alongside people must communicate intent clearly. Subtle cues in motion, posture, and timing convey awareness and predictability. As interaction models mature, collaboration becomes intuitive rather than forced. Humans adjust their behavior naturally, treating the robot as a reliable co-worker rather than an unpredictable machine. And training and deployment are streamlined through centralized updates and configuration. Instead of manual programming at each site, improvements propagate automatically. This reduces complexity and ensures consistency across deployments. It also enables rapid response to new requirements, as software adjustments can redefine behavior without physical intervention. And over time, specialization emerges through software profiles rather than hardware variants. A single platform can serve manufacturing, logistics, healthcare support, or domestic assistance simply by adjusting objectives and constraints. This versatility maximizes utilization and accelerates learning as diverse experiences enrich the shared intelligence base. And the working Tesla bot represents a broader shift in how intelligence is valued. Intelligence becomes an infrastructure component as fundamental as electricity or connectivity. When intelligence can be deployed physically, its impact extends beyond information processing into the realm of action. This transition unlocks new possibilities for efficiency, safety, and human empowerment. And continuous improvement remains the guiding principle. Each limitation identified becomes a roadmap for the next iteration. Progress is measured not by perfection, but by momentum. Small gains accumulate into transformative capability when pursued relentlessly. This mindset ensures that development remains grounded, adaptive, and resilient in the face of complexity. And as intelligent robots integrate into daily operations, they begin to reshape expectations of what is possible. Tasks once constrained by human endurance become routine. Environments adapt subtly to accommodate collaboration, not through redesign, but through shared understanding between humans and machines. This mutual adaptation marks the beginning of a new phase in technological integration. And the reveal of a working Tesla bot is not a destination, but a signal that the journey is underway. It demonstrates that advanced AI can inhabit the physical world responsibly, efficiently, and at scale. Each deployment strengthens the system, each interaction deepens understanding, and each iteration brings the technology closer to fulfilling its potential as a practical, trustworthy partner in human progress. And this progression reshapes expectations around what machines can contribute to society when intelligence is embedded directly into physical capability. A system that can perceive, reason, and act in the same environment as humans becomes a multiplier of effort rather than a replacement. The value lies in amplification. One person overseeing multiple intelligent machines can achieve outcomes that once required entire teams, not by working harder, but by working smarter through coordination and intent. And as deployment expands, diversity of environments becomes a training asset. Warehouses, factories, offices, and semi-structured spaces each introduce unique challenges. Floor surfaces vary, lighting changes throughout the day, objects differ in shape and texture, and human behavior remains inherently unpredictable. Exposure to this diversity strengthens robustness. The system learns not just ideal conditions, but edge cases exceptions and rare events. Over time, this breadth of experience builds resilience that no controlled laboratory environment could replicate. And precision improves alongside confidence. Early movements prioritize safety and caution, favoring slower execution with wide margins. As perception sharpens and prediction improves, motion becomes more fluid and efficient. This is not about mimicking human motion for its own sake, but about achieving reliable outcomes with minimal energy and maximum control. Every improvement reduces friction, both physical and operational, making integration smoother and more intuitive. And the architecture supporting this intelligence is designed for continuous evolution. Neural networks are modular, allowing specific capabilities to be upgraded without destabilizing the entire system. Perception planning and control layers evolve independently yet cohesively. This modularity enables rapid experimentation, where new approaches can be tested, validated, and deployed incrementally. Progress becomes steady rather than disruptive, preserving trust while advancing capability. And data plays a central role, but data alone is not enough. What matters is relevance, quality, and feedback. Each interaction generates labeled experience through outcome evaluation. Success reinforces behavior while failure becomes a lesson. This closed-loop learning accelerates improvement and reduces the gap between simulation and reality. The system does not merely repeat tasks, it understands why outcomes differ and adjusts accordingly. And the broader ecosystem benefits from this approach. Tooling, infrastructure, and workflows evolve in response to intelligent automation. Standardized interfaces emerge, making collaboration between humans and machines more seamless. Over time, best practices spread, lowering the barrier to adoption and encouraging innovation across industries. This ripple effect extends impact far beyond the robot itself. And trust remains a cornerstone. Transparency in behavior, predictable responses, and consistent performance build acceptance. When people understand what a system will do and why it will do it, collaboration becomes natural. This trust is earned through reliability over time, not through promises. Each successful interaction reinforces confidence, paving the way for expanded responsibility. And the adaptability of software-defined behavior introduces a new model for deployment. Instead of fixed function machines, a single platform evolves with demand. Seasonal workloads, shifting priorities, and unexpected challenges can be addressed through updates rather than replacements. This flexibility reduces waste, conserves resources, and aligns technology with real-world needs that are rarely static. And as capability grows, ethical considerations remain integral. Decisions about autonomy, data usage, and human oversight are approached with caution and intent. The goal is alignment with human values, ensuring that technology serves collective well-being. Safeguards, audits, and human-in-the-loop mechanisms maintain accountability as systems become more capable. And the implications extend into areas where human presence is limited or risky. Disaster response, hazardous material handling, and remote operations become more feasible with intelligent machines that can operate under conditions unsafe for people. These applications save lives and expand reach, demonstrating value beyond efficiency alone. And learning curves accelerate as familiarity increases. What initially feels novel becomes routine, and routine becomes expected. This normalization of advanced capability marks a shift in baseline assumptions about productivity and support. Once integrated, the absence of such assistance feels like a limitation, underscoring the depth of impact. And the convergence of hardware, software, and data creates a self-reinforcing cycle. Better hardware enables richer data improves software, and improved software extracts more value from hardware. This synergy compounds over time, driving exponential rather than linear progress. Each generation benefits disproportionately from the foundation laid by the previous one. And global scalability introduces new perspectives. Different regions present distinct constraints and opportunities, from infrastructure variability to cultural expectations. Exposure to this diversity further refines adaptability. The system learns not just physical variation, but contextual nuance, enabling more sensitive and effective interaction across environments. And education and training evolve alongside deployment. As intelligent robots become commonplace, understanding their operation becomes a fundamental skill. This does not require deep technical expertise, but an intuitive grasp of collaboration and oversight. Empowering people to work effectively with intelligent systems democratizes benefit and reduces friction. And over time, the distinction between tool and teammate blurs. The robot remains a machine, but one that understands context, anticipates needs, and responds constructively. This relationship enhances efficiency without eroding human agency. Control remains explicit while assistance becomes implicit. And the long-term vision centers on abundance. When physical labor constraints diminish, resources can be allocated more freely toward creativity, exploration, and problem-solving. Automation becomes a pathway to higher quality of life rather than a threat to it. This outcome depends on thoughtful deployment, continuous improvement, and alignment with human priorities. And each milestone achieved reinforces confidence in tackling the next challenge. Balance leads to agility, agility leads to dexterity, dexterity leads to complex manipulation. Perception evolves into understanding, understanding into anticipation. These transitions are gradual yet transformative, reshaping what intelligent machines can accomplish. And the working Tesla bot stands as evidence that this trajectory is not theoretical. It demonstrates that intelligence can inhabit form, that software can guide motion with purpose, and that learning systems can adapt to the real world. Progress continues through iteration, data, and disciplined engineering, advancing capabilities step by step, as intelligence and utility grow in parallel.